Now, as I said, there is an alternate method of working out the area of the circle by dividing the pizza or the circle up into small slices, right? So this is how we're going to divide it up. And so if we take out one slice, this slice will look sort of like this, right? I'm not an artist, I'm sorry, it doesn't really look like a proper slice. Maybe I could try to correct it. So at least it doesn't look as bad. All right, that looks better, sort of. So we could try to work out the area of an individual slice, right? And in order to do so, what we're going to do is we're going to approximate it as triangles. So we're going to, draw this line here. And rather than working out the area of the entire slice, we're only going to work out the area of the triangle that goes under it, that goes inside the slice, like that. Now, each of the slice, of course, will take up an angle of theta. And if you take a look, this length here will equal to r. So if we chop this part off, what we'll get is we'll just get a triangle looking somewhat like this, right? Not to scale, sorry about that. Again, this angle equals to theta, this length equals to r. And then you can work out the length of the other two angles. This one will equal to r sine of theta, and this one will equal to r cosine of theta. And what you can do now is you can work out the area of the triangle. The area will equal to half base times height. And if you just take this as the base and this is the height, this will equal 2r squared divided by 2 times sine theta cosine theta, like that. But now we will be doing some really dirty approximation. So this next minute or so might anger a lot of people, but we're going to do it anyways. So now let's imagine the triangle becoming really thin, sort of like this thin or something like that, or even thinner, right? This angle is still equal to theta, but now we can do some approximations with the other two sides when we keep this side to equal to r. We can approximately see that this side will be approximately equal to r, right? And that also works because as theta goes to 0 or closer to 0, cosine of theta will get closer to 1. So r cosine theta will get closer to just r. And for this side, well, we're going to be doing this wonderful approximation where sine of theta will approach theta. I think most of us are probably aware of that. So this side will be approximately equal to r theta. And so now we can reevaluate the area of each individual triangle. And that will equal to half r squared theta, like that. But that's not all. We could make this slice even smaller, even really, really small. I think that's the same side, but you get my point. So now theta is really small. And as theta becomes really, really small, the theta itself turns into d theta, or an infinitesimal amount of the angle. The slice becomes so thin. And so now the area, or in fact the really small area, dA, will equal to half r squared d theta. And so what we have done is we have worked out the area of each individual, well, small slices. And so if we divide the circle up into really, really thin slices, like really, really thin, this is a really bad diagram now, one slice, one really small slice of the circle could be approximated with the area over here. It will approximately equal to 1/2 r squared d theta, where d theta is this really tiny angle of the circle. So now that we have the area of each individual slice, we can work out the area of the circle. And the area of the circle will be the infinite sum of these small pieces. So the area of circle will be an infinite sum, or the integral, of each individual small area, or dA. That's an A. That's an A. And that will equal to the integral of half r squared d theta. And where are we integrating from? Well, the first slice will have to be at 0, right? At 0 radians. And we want to evaluate this integral for all the slices all around the circle. So if the first slice starts at 0, we would have to go all the way around the circle, one loop, and then that's where the last slice will be. And so we go around one loop, that's going from 0 radians all the way to 2 pi radians. So that's going to be our limits of the integration. We have to integrate from 0 all the way to 2 pi, like that. And so this could be integrated rather easily, right? Because in this case, we're integrating with respect to theta. And so you can take half r squared as a constant. So you could just write half r squared like that out as a constant, and then integrating from 0 to 2 pi with respect to d theta like that, and you could verify by yourself that this will in fact come out to pi r squared. I won't show you how to integrate that, but that should be pretty obvious. And yeah, so there it is. That's another way you can prove the area of a circle rather easily. And so that's another method where you can find the area of the circle by dividing up the circle into small slices.